So that means I can start from basics. So are you comfortable looking at this text? Is it too small or okay? Many colors, huh? What we can do is that we can make it a little big. Is it better now? We call it a contingency table. Before we jump into naive Bayes, let's give names to these colors. Let's say on here we have a factor that we are going to use to predict an outcome. This is our response variable or target variable. Factor X can have two values, X1 and X2. Outcome is binary, Y1 and Y2. Now in these cells, we count how many times we see X1 with Y1, how many times we see B with Y2, how many times we see this and this together. That means on the margins of this table, we will have sum of A plus B, C plus D. On here, A plus C, B plus D. We can convert this counts table into probabilities table by just taking some fractions. A divided by total number of observations is going to give us the joint probability of observing X1 and Y1 together. So in these four cells, we have joint probabilities. Correspondingly, on the margins, we have marginal probabilities. Joint, marginal. In probabilistic notation, we write it like this: probability of X1, Y1. Right? Joint probability. The marginal probability we will write like this: probability of Y1, probability of Y2, etc. Now let's apply them to a problem. The problem is we have observations about 40 patients. We observed one symptom, sneezing, not sneezing. And based on that, we want to predict if person has cold or flu. You can see 15 people have cold and they are sneezing. Similarly, 14 people are diagnosed with flu condition and they are not sneezing. We convert them into probabilities like this. So our joint probability of observing a person with sneezing symptom and cold diagnosis, it is going to be calculated how?
X over total of.
That's right. This number divided by total. We go back to our definition slide. We can see here A joint probability is A over total. A over T, B over T. On the other hand, if we want to calculate the marginals, we will just add these two numbers. We will get marginal probability of sneezing. What is this number? Marginal probability of cold. Right? So these two probabilities, joint probability and marginal probability of joint probability of two events, marginal probability of one event, they are very interestingly related. We can ask interesting questions. For example, what is the probability that somebody is sneezing given that the person has cold? So given information is after this pipe sign. Given that the person has cold, we know the person has cold. What is the probability person is sneezing? How shall we calculate? Numerator is joint probability of sneezing and cold. And denominator is the marginal probability of the known information. What we are asking, what is unknown, is how likely is that some person is sneezing, given that we know the person has cold. Now, this probability is called conditional probability. Probability of sneezing conditioned on cold. Overall, in the data set, people are sneezing. The probability of any random person sneezing is 0.52. But if that person, we know the person has cold, that added information will change this probability of sneezing. It will increase or decrease. And we will calculate that by dividing the joint probability of both events, dividing this by the marginal probability of known event. Known is what? Cold. Person has cold. We know this. 0.75. You can see when we don't know the person has cold or flu, the probability of sneezing is 0.525. But when we know the person has cold, it changes to 0.75. When we know the person has flu, it will change to 0.3. See? Joint of sneeze and flu divided by flu. Make sense? So this probability is conditioned on class. We call it class conditional probability. It is, in fact, giving us the likelihood of observing a symptom given that we know the class of the patient. Patient belongs to cold class. And this is learned from the data. Right? So we have prior, we have joint. Sorry, I wrote prior instead of prior. Let's call it marginal for now. I didn't introduce you to prior yet. Marginal probability, you know what it is. It will come from the margins of the table. Joint probability, you know what it is. It is coming from these counts divided by total. The ratio of marginal and joint is conditional. Conditional is equal to joint probability divided by marginal. Okay. So far, just three things: joint, marginal, their ratio is conditional. If you keep in mind these three things, you will master the technique that we are going to learn. They have this relationship, right? So if this equation is what we have, that means joint will be equal to marginal multiplied by conditional. Would you be comfortable with that? Right? This marginal goes to the other side and multiplies. So multiplying marginal with conditional will give us joint probability. You want to verify that? Okay, let's go ahead. Look at here. The conditional probability, 0.75. If we multiply it with the marginal probability of cold, which is 0.5, we will get 0.375. Which is same as the joint probability, right? Now we know that joint by marginal is giving us conditional, conditioned on the known information. So can I change the position? Instead of having S given cold, can I ask, what is the probability of cold given S sneezing? It will be the joint probability of S and cold, divided by margin of known information, sneezing. What is the probability of sneezing? 0.525. Joint, 0.375. So the same ratio, same formula, just changing the marginal probability gave us the corresponding conditional. Conditioning on what? Whatever we are conditioning on is going to be the denominator for marginal. And that will answer two interesting questions, right? Now, if you see, we just did classification. we just did classification of somebody who is sneezing. What if we see somebody sneezing? What is the probability the person is having flu? We will calculate it by the joint probability of sneezing and flu, dividing it by probability of sneezing. If probability of cold given sneezing is greater than probability of flu given sneezing, we will say the person is having cold, and vice versa. So classification done. Now let's name them, these things. We are going to, do you have any questions so far? All good. Now I'm going to call this probability where we want to classify somebody who is sneezing, which class it belongs to, cold or flu, right? These two probabilities are our posterior probabilities. We call them posterior because we estimate these probabilities after knowing the fact of symptom. After knowing the value of input X, we want to predict the value of Y, right? Our target variable is diagnosis. We want to predict class of target given input. After we know the input, then we predict post evidence, right? Post evidence. That's why we call it posterior probability. Would you agree with this name, posterior? So in a way, posterior is a new word here. It is a conditional probability where we are asking about the class given input. It is equal to what? It is equal to, it should be equal to the same thing, joint divided by margin, right? Joint divided by marginal. Marginal of what? Marginal of X. The next name that I want to give is, I want to name these two marginal probabilities. The marginal probability of class being cold, or the marginal probability of the class variable being flu. The marginal probability of a randomly picked person out of these 40 patients. What is the probability a randomly picked person will have cold? 0.5, right? So we want to estimate what? Whether the person has cold or flu, right? So if we don't know any information about the symptom, prior to knowing the symptom, what is our prediction about cold? 0.5. What is our prediction? If we don't know the person is sneezing or not sneezing, we don't have any input, any evidence about symptom, we will just calculate probability of cold from this margin, which is 0.5. So since we calculated prior to the fact, prior to knowing the fact of input, it is going to be called prior probability. Second new word, posterior, prior. Now third new word is likelihood. Likelihood is what? We will change the question. If our posterior is asking whether the person has cold, given that the person is sneezing, we will change the question. We will say, person, what is the probability that person has sneezing given that person has cold? So given information is changed, right? We change the position. When we change the position, knowing the class, estimating X, we are going to call this conditional probability likelihood. Likelihood of observing an input X, given that we know the output. Likelihood multiplied by prior is what? You know, we did that. My prior multiplied by likelihood is joint probability of sneezing and cold, divided by margin of what? Margin of sneezing. This is the information that we have, right? margin of sneezing, margin of sneezing. That means the posterior probability is equal to likelihood multiplied by prior. Multiplying likelihood with prior is joint probability. Divided by this, marginal. So marginal of symptom is going to be called total evidence. Why? Because we are combining, we are adding the probability of sneezing. Probability of sneezing is distributed in cold class and flu class. We are going to combine them together. 0.375 plus 0.15 is probability of sneezing. It is the total evidence. So likelihood multiplied by prior divided by total evidence is going to give us the answer. So again, 4 things. Your question, what you want to predict. You want to predict the class. The probability of class given the input is posterior. Probability of input given class is likelihood. Probability of class itself is prior. The denominator is total evidence. These two guys, total evidence. I'm going to clean it up and I will ask you to help me rewrite it. So if I say, what is the probability of person having cold given that person is not sneezing? You will do what? We can look at the joint probability of not sneezing and cold divided by the marginal probability of information that we have. Now we can expand it. This joint probability is likelihood of not sneezing given cold multiplied by probability of cold divided by the total evidence of not sneezing. So posterior is equal to likelihood multiplied by prior divided by total evidence. Now, this formula is, I didn't create it. It is as old as 1885 or around that area, around that time, formulated by Thomas Bayes, the great statistician. Thomas Bayes connected these conditional probabilities with marginals and joint probabilities to be able to ask this question. That is why we call it Bayes formula. And when we do classification with Bayes formula, we say we are doing Bayesian classification. Now suppose that your input is more than one. You have 2 or 20 inputs, not just sneezing or not sneezing. You are also measuring temperature. You are also measuring what the person ate in the morning. You are also measuring temperature maybe or whatever. How will you predict? The answer is simple. Probability of cold given x1, x2, x3, as many inputs as you have, will be equal to probability of x1 given cold, probability of x2 given cold, multiplied by probability of x3 given cold, multiplied by probability of cold, divided by probability of x1, x2, x3, whatever the inputs we have, their marginal probability, total evidence. But here is the catch. Sometimes these inputs are correlated. For example, if somebody is sneezing, maybe it is more likely the person also has temperature, and maybe it is more likely that person has some other symptom that we are measuring. But if we look at those correlations, then we cannot apply this formula. We need to apply chain rule of probability. But to be able to simplify our computations and be able to apply this formula, we make a naive assumption that all inputs are independent. Due to this naive assumption, we call this formula naive Bayes formula, which doesn't mean that when Thomas Bayes was naive, he was genius, but naive Bayes formula is naive Bayes because of our assumption that all inputs are x1, x2, x3, x4. They are all independent. Naive Bayes is should be the first algorithm that you implement and get the benchmark minimum possible error that you can get. Minimum possible accuracy, right? Any other more sophisticated, more complex algorithm should be measured against what? We will measure it against naive Bayes. So naive Bayes is your first step in any analytics project. You construct naive Bayes, that gives you baseline performance. On top of that, you build when you build other models, you fit other models, you compare them with naive Bayes. Any questions so far?